depending on where you guys did your organic chemistry, it's possible that you did some carbohydrates already. Maybe you did, maybe you didn't. Carbohydrates can be pretty complicated, but all the chemistry that's involved in carbohydrates is stuff that you did have in organic chemistry at some point along the way. So as we go through, start going through this material, I'm going to draw on it and remind you of the functional groups and certain kinds of reactions that they do. So carbohydrates are a very diverse group of polymers known as polysaccharides. But there are important versions of carbohydrates that are the monomer version, so monosaccharides and disaccharides, oligosaccharides, and polysaccharides. So we'll talk about all of those. They're very diverse in terms of their roles in cells as well. So we'll talk about that a little bit more as we go. So we're going to start with the monosaccharides, which are the monomers that make up the polysaccharide forms of these molecules. One way to talk about carbohydrates is that they are polyhydroxy aldehydes or ketones. So, going back to your OChem, alcohols, aldehydes, ketones. Okay, so that's most of the chemistry that's going to be involved with carbohydrates. And the most common sizes, because they can come in different chain lengths, are those that have 6 carbons. And a general name for monosaccharides that have 6 carbons is hexose or hexoses. So you guys just finished a chapter on enzymes. What is the suffix of an enzyme name usually? ACE, right? ASE, ACE. It's a good crossword clue if you're looking for crossword puzzle. So carbohydrates, saccharides, it's OSE, OSE. Okay, so the suffix of carbohydrates is OSE. Most common is 6 carbons, but there's also some very important 5-carbon monosaccharides, like the ones in our DNA are 5 carbons. So those are pentoses. And then the 3-carbon monosaccharides, there are several of those too that are very important. And those are called trioses. So the main, the carbonyl functional group is one of the ways that we categorize monosaccharides, so not just their chain length, but which carbonyl functional group they have. So that's going to be either an aldehyde, in which case we have another general term for the sugar, and we call it an aldose. Or that carbonyl functional group can be a ketone, in which case we're going to call it a ketose. So by now you guys know that in biochemistry, biochemists like to throw a lot of lingo around, right? So these are just different names that will come up when people are talking about monosaccharides. So if somebody says aldose, okay, you know what that means. It means a sugar that has an aldehyde carbonyl functional group, okay? So a couple of primary examples of that. So of the aldehyde, so a common aldose is glucose. And a common ketose is fructose. And I'm sure that he's going to be asking you to memorize these structures. So I'm going to go ahead and draw them for the first time. The only way you can memorize a structure like this is to draw it over and over again until you can take a blank sheet of paper and draw it and boom, you're done, right? Okay, so glucose, there's our aldehyde functional group. And I'm drawing this in a chain form. We're shortly going to be drawing it in a ring form, okay? So it has 6 carbons. We're going to use a Fischer projection formula to do this. So carbon 1, 2, 3, 4, 5. Now you guys, you probably did some Fischer projections with amino acids, right? Earlier in the semester, did you use Fischer projections with your amino acids? Some people are nodding and some people are looking at me blankly. So I'm going to take that as a yes. And I'm going to go ahead and put in a bunch of HOH groups on here. Okay, so this is glucose. Actually, this is specifically D-glucose, and we'll talk in a minute what that D actually means. Now, I'm going to give you guys a little hint right now, is that it will make your life so much easier to memorize all of the monosaccharides that he's going to ask you to memorize if you memorize this one first, because all the other ones can be variations on this. So this is D-glucose. D-fructose, the only thing we're going to do to get fructose is we're going to swap the position of this carbonyl group. That's all we're going to do, okay? So that means that carbon number 1 is going to become an alcohol. So I'm going to go ahead and drop that. So carbon number 1 becomes an alcohol. Carbon number 2 becomes a ketone. Can't be an aldehyde because it's not on the end of the chain, right? So it's a ketone. And then everything else is exactly the same. So I'm just going to go ahead and draw that in. Carbon 3, carbon 4, carbon 5. Okay. And that is D-fructose. One other example I'm going to give you, because it's something that's very common and comes up a lot before we move on, is this is of an aldotriose. So I'm combining 2 general terms here. It's called this aldotriose. And the example that we're going to use is D-glyceraldehyde. Again, using a Fischer projection. So this is just a 3-carbon aldotriose. An aldose because it has the carbonyl as an aldehyde. And the D will explain that next. So one of the things that can make carbohydrates kind of difficult to study and understand is their stereochemistry. So you guys, having had organic chemistry, know something about stereochemistry. You know what a chiral carbon is, what achiral means. Carbohydrates, especially the ones with 5 or 6 carbons, they have a lot of chiral carbons. And each of those chiral carbons has 2 different stereochemistries that it can have, right? So that adds up to a lot of different possibilities. So I'll give you an example. So we have D-glyceraldehyde at the top there, a couple of 4-carbon sugars, some 5-carbon sugars, 6-carbon sugars. Okay, so with the 6-carbon sugars that have an aldehyde at the top, of the D version, there are 8 of them. There are also 8 L sugars. Okay, so 16 different isomers. And remember, these guys, they're all structural isomers of each other. They're stereoisomers. They all have the same molecular formula, right? They just differ by which configuration each of these chiral carbons has. Okay, so he's not going to ask you to memorize all 16 of these. So you'll memorize glucose, and that'll be kind of your reference 6-carbon carbohydrate that you use to talk about other versions. Okay, so we have what we call the D and L configuration. I'm sure you guys did this with amino acids, right? Because what does the body have the most of, D or L?
D.
Remember?
D.
L, right. So we have mostly L amino acids. We have mostly D carbohydrates. Okay? And how we tell the difference between these two is actually pretty similar to how you did it with the amino acids.
Can you zoom out?
Sorry, I'm going to have to readjust this every time. It looks like. Okay, so glyceraldehyde just has one chiral center. So we're only talking about 2 enantiomers. Okay, so guys, remember what's the definition of an enantiomer? Non-superimposable mirror image isomers, right? So non-superimposable mirror image isomers. Who remembers what a diastereomer is? What's the definition of a diastereomer? Start the same way. Non-superimposable, non-mirror image isomers. Very good. Okay, so you're going to be doing a lot of that with the carbohydrate. So these are enantiomers. Non-superimposable mirror image isomers are enantiomers. Okay. By convention, when the H is on the left, that is D. When the H is on the right, that is L. Okay. So this is D-glyceraldehyde, this is L-glyceraldehyde. Now, I'm always looking for ways, because biochemistry, there's so much to absorb there, and I don't want to memorize one single thing I don't have to memorize. So I'm going to point out to you guys that this is actually pretty analogous to how you did it with the amino acids. If we make the carboxyl group of an aldehyde be analogous, okay? And if we make the OH group be analogous to the amine, then you can see the similarity, okay? So would this be an L or a D amino acid? An L, right? So an L amino acid was when the carboxylic acid was at the top and the amino on the left. The L carbohydrate is when the aldehyde is at the top and the OH is on the left. Okay? Okay, so that's great. What are we going to do when we have a bunch of chiral centers? Then what do we do? Okay, so if you have more than one chiral center, how can we deal with that? So we'll use glucose as an example. Keep using glucose because by the time you draw this thing over and over again, You're not gonna have to memorize it, because you'll already know it. Okay, well, we just said it's D if the H of the chiral carbon is on the left. So I got 4 chiral carbons to look at, right? So I have to know exactly which chiral carbon I'm talking about. And the one we're always going to be talking about to tell whether it's D or L is the one, it's basically the next to the last one in the chain, okay? So another way to think about it is this carbon is the only primary alcohol that's in the molecule. So it's the chiral center next to the primary alcohol. I don't usually think about it that way. I just think, oh, it's the next to the last one. Okay. Can't be the last one. Why can't it be the last one that we're looking at? It's not chiral, right? Yeah. So it's the chiral carbon that's furthest down the chain. That's what we're looking at. Okay, so this is telling us, this is the one that tells us that it's D. Back to the PowerPoint for a second. Because now, if we look at all these 6 carbon sugars here, every single one of them has that configuration. Okay? So, if these were swapped on any of these, it would be an L sugar. Okay. Okay, now, because we don't have enough terms, I'm going to give you another one. Okay, so we just said we just had definitions for enantiomers and diastereomers. And biochemists, not being satisfied with simple language, always wanting more and more terminology, we also have to talk about epimers, okay? So we had a definition for enantiomers. We had a definition for diastereomers, which I'm not going to write here. Look it up. If you couldn't immediately write that down, go ahead and review that. That's kind of basic stuff. Okay, so an epimer, epimers are diastereomers, or you just, yeah, I suppose it all includes diastereomers. Diastereomers that differ by one chiral carbon. Okay, so again, we'll go back to the PowerPoint. So differs by one chiral carbon, okay? So here's D-allose, D-altrose. Are these guys epimers? What do you think? Yeah, they are, because they differ by one chiral carbon. Okay, so these are epimers. What about these two guys? Are these epimers, allose and glucose? Yes, they are, right? Because they differ by one chiral carbon, right? Okay, what about these two guys? Are these epimers? No, because these differ by 2 chiral carbons, okay? So if you have nothing better to do, you could, this figure is probably in your book, you could sit down with a pencil and, okay, these are diastereomers, these are enantiomers, these are epimers. You can kind of drive yourself crazy doing that. But if you take the time to go through and do that, then you know you understand it, right? You know what the difference is between all of those stereoisomers. So it might be worth doing that. Okay, so monosaccharides don't just exist as chains. The longer ones don't just exist as chains. They also exist as rings. So 5-carbon and 6-carbon monosaccharides can form rings. You kind of already knew this anyway. Now, before we get into that, I want to review a little organic chemistry because it will make your life easier when we start doing this to make the rings, okay? Okay, so review of hemiacetals, etc., because that includes hemiacetals, acetals, hemiketals, ketals. So we'll go over each of these, and then we'll apply it to forming a ring. So a hemiacetal forms in a reaction between an alcohol and an aldehyde. Now, if you were going to do this in a test tube, you'd have a little acid in there. In the body, not how it's done. In the body, an enzyme, right? Would facilitate it. And what we're going to do is an addition. So this is not a substitution reaction, it's an addition reaction. Okay? Nucleophile, this oxygen is the nucleophile, comes over here. No leaving group, right? You can can't kick off that hydrogen as a leaving group. So this pair of electrons is going to find an H+, which are floating around all over the place in water, right? And what that's going to make is this guy here, which is a hemiacetal. Okay, that's pretty straightforward, right? It's just a simple addition reaction with a nucleophile attacking carbon, no big deal. I can actually do it again. Under the right conditions, I can now do a substitution between another molecule of this and this, okay? So if I add in another one of those guys, then this can attack this carbon, which is kind of a hidden carbonyl, actually. And we can kick this off. Now we do have a okay? So if I do that, then I'm going to end up with...
Do you propane that OH?
Yeah. Oh, I'm sorry. Oh, you were telling me that. I'm sorry?
We need to propane that OH first, right?
Yeah. Yeah. Yes. I'm not going to ask you guys to follow all the steps of the mechanism, but you're right. So what he said was you protonate the OH first and make it a better group, right? Okay. So I'm going to put another one of these on there. I'm still going to have the H, and I'm still going to have the R2. And that is an acetal. Now, again, because I'm a person that doesn't want to memorize anything I don't have to memorize, rather than memorize what a hemiacetal is and what an acetal is, just understand the reaction, right? And you don't have to memorize it. And And I can give you any alcohol and aldehyde, and you can play out. Okay, so we're going to do the same thing with a ketone, and I'm going to start it for you, but I'm going to let you guys finish it on your own. So I can do the same thing with a ketone. In fact, why don't you take a minute to just go ahead and do it. I see lots of arrows doing the right thing. So yeah, we're going to have that nucleophile come over here. This is going to grab a proton, and I'm going to end up with this guy. And this is a hemi ketone. If now I go ahead and do a substitution with that OH group, and then I'll have a ketone. Okay. It is worth your time to go back and make sure you understand how to do these reactions. It'll just make it easier for you in the long run. Okay, so now let's apply this to forming a ring. We'll go back to glucose. The third or fourth time we've drawn that guy. Not the last. If after lecture, sit down and draw it on a piece of paper 4 or 5 times. Okay, we need a carbonyl and an OH group. Okay, we have a carbonyl. We have a lot of OH groups. Okay, so how do we know which OH group we're going to be using? And the answer to that is that it's usually going to be the secondary alcohol that's furthest away. Doesn't have to be, though. And I would torture my 160A students by asking them to draw rings using different OH groups along the chain. So for glucose, it's going to be this one. So here is our nucleophile. And we're doing exactly the same reaction we just did. Exactly the same. We have to kind of envision in our heads, you know how all these bonds here at each of these carbons, they can rotate around, so the chain can rotate itself around, so that this OH group is pretty close to that carbonyl. Okay, that's possible, hard to draw on paper. So I'm just going to indicate it comes over here. Again, that is going to have to pick up the proton. And now I'm going to magically end up with something we call a Haworth diagram, which here's where we depart from the organic chemist, right? Because the organic chemist would say, we're not drawing that, we're drawing chairs, okay? And if Dr. McReynolds were teaching this class, you would be drawing chairs. Because she's a true organic chemist. And the rest of us, biochemists, should probably draw chairs too, but we feel we have enough work to do, so we're just gonna go with the hot instruction. Okay, so let me put the rest of this in. Okay, so second thing you should waste no time in memorizing is this ring. So you have the chance glucose memorized, the ring of glucose memorized, and everything else is going to be in reference to that. Okay? So let's go ahead and interpret this. How did we end up with this thing from here? Okay? So carbon 1, 2, 3, 4, 5, 6. Okay, so you guys tell me, where is carbon 1? And how would you know which one it is? Where is carbon 1 in that ring?
Rightmost point.
Okay, so it's this one right here. This is carbon 1. Okay, how did we know that? How did we know that's carbon 1?
Because the OH it works out instead of actually being well.
Well, it's a hemiacetal, right? Is that what you're saying basically? It's the hemiacetal, okay? So, it's got oxygen. It's got to have an oxygen bonded to it, right? Because we attacked it with oxygen, okay? We know we made an OH group there, and then it's attached to the rest of the ring. Okay, where's carbon number 6? Carbon number 6 is the one sticking up. Okay, so once you know that, then you know what the rest of them have to be, right? I can't go to 2 here and then go to 6. That wouldn't make any sense, right? So it has to be 2, 3, 4, 5, and 6. And this is the hemiacetal. Okay, now, again, to make our lives easier, one way to remember this is if I take this guy and I turn it this way on its side, okay, then the number 2 OH points down, the number 3 OH points up, and the number 4 OH points down. Okay. You know who I learned that from? Dr. McReynolds. Seriously. I taught this material for I don't know how many years, and I just remembered, oh, if it's on the right, it's down, if it's on the left, it's up, and I had this mnemonic to help you remember. And one day, I don't even know what we were talking about, she said, oh yeah, you just do this. And I'm like, yeah, okay, how easy is that? Okay, so now I should be able to give you any chain. Go ahead and do one for the heck of it. And I'll do a D sugar because it gets a little bit more complicated with an L sugar. Not that complicated, but it is a little different. Okay, there's a D sugar. Okay, draw me the ring. And I would always start, just make the ring with the oxygen in the upper right. All D sugars have that last carbon pointing up. It's always going to point up in a D sugar. If I think about flipping this guy over, okay, this is 2, 3, 4, 2, 3, 4. They're all going to be what? Pointing up or down? Up. Yep. Okay, so up, up, up. Okay, what do we do with this guy?
The OH points down.
Because actually, we could, right, we could do this, or we could do something else, and so we're going to talk about that next. Right now, you could do it either way, and I would say it's correct. All right, so now you know how to convert from a chain to a ring. Ring to chain is going to be just as easy. You find your carbonyl group, you count the carbons, that's the last one in the chain, put it on the right side, right, depending on whether it's up or down, and it'll be just as easy. Okay, let's see, where does he do alpha? Okay, so we'll just go ahead and do that now. So alpha versus beta. Anomeric carbon. What was the carbonyl carbon is called the anomeric carbon. Okay, so the anomeric carbon equals the carbonyl carbon. And because of the ability of those, this carbon number 2 to rotate around, how that OH group attacks the carbonyl might give you 2 different configurations here, okay? So if the OH is pointing down, then we have an alpha configuration. If, when the ring is closed, the OH is pointing up instead, we have a beta configuration. And it's really important to keep track of that, because having an alpha versus a beta configuration, when a bunch of glucoses are strung together, is the reason we don't digest wood. Okay? So that will be explained when you guys talk about glycogen versus cellulose, but that's the main difference between glycogen and cellulose, is whether the sugar was alpha or beta when they came together to form polysaccharides. I think it would be really cool if we could digest wood, but actually we can't, because we can't digest polysaccharides that have glucose in that beta configuration. Okay. Glucose in a mildly acidic solution can interconvert between all of those forms. And that is called immunorotation. So this is the interconversion of chain and ring forms. Of a monosaccharide.
What does that first word say?
I'm sorry?
What does the first word say?
Mutarotation.
I'm still wondering if you said, sorry.
I'm sorry, what? Interconversion. I didn't draw my O there. Interconversion of chain and ring form. So have the chain. And I'm using glucose as an example, but this can happen with other sugars too, etc. I'm not going to draw the rest of it. So this can go into the alpha ring of glucose, or the beta ring. Okay, and what I mean by that is the glucose ring with all this correct groups showing here with the OH down, or the OH up. Enzymes can speed that up in the body, but if you had glucose in a mild acid solution, it could do this. It could interconvert. There'd be an equilibrium between all of these. Okay, so once we're talking about rings, now we have yet another set of terms to deal with, and that is the difference between pyranoses and uranoses. Okay? So this comes from these molecules here, which you probably encountered in OChem. So this is paran, and this is uran. So basically, what this tells us is that a pyranose is a six-membered ring. Six-membered ring. Sugar, right? The sugar with a six-membered ring. And furanoses are five-membered. Okay, more terminology. Now that we know this, the alpha ring form of glucose is, we don't call it D-glucose anymore. D-glucose is what we call the chain. We would call it alpha D-glucopyranose. Alpha D-glucopyranose. So glucose, D is a D sugar, alpha, the OH is down, pyranose is the 500 ring. Okay, so that's a pretty decent system of naming. We couldn't use the IUPAC system of naming these things. Well, we could, but nobody would want to. So we're going to use this system instead. Okay. So we looked at how glucose forms a ring. So to wrap things up, let's just take a minute to think about what would happen if fructose formed a ring instead of glucose. Yeah.
Can you actually switch down to the third, last part of the previous page?
Uh-huh.
Thank you.
You're welcome. Okay, so same reaction. This OH group is going to attack that carbonyl. This is going to become, this oxygen will become an OH. this oxygen will be in the ring. And I'm gonna go ahead and just draw the 5-membered ring. And I'm gonna say, let's make it beta D fructose uranose. Uranose because it's 5-membered. Okay, carbon 2, not carbon 1, because the carbonyl is on carbon 2. And it's beta, so I'm going to make my OH go up. That's the carbonyl oxygen, I'm going to make it go up. The other thing on here, not a hydrogen, it's carbon 1. And then 3, 4, 5, 6.
Does the token strategy work here?
Pardon me?
Does the token strategy work here too?
Yeah, so the alpha beta is always referring to what the OH is
I'm
doing.
talking about when you did with the 6 carbon one, so you flipped it over and.
Oh, yes, so that's next. Okay, so the other OHs, same thing. Flip that guy over. So this is 3, 4. So what's 3 doing, up or down? It's up, right? And 4 is going to be down. So if you think it would be helpful, I can scan these and give the file to Dr. Savage to put on SACCT. You guys probably have more notes at the end than what I wrote in, but